tank circuit. And this is very interesting because I can take an oscillator against this, and the oscillator, if it's not quite in sync with this tank circuit,
resonant frequency of the tank,
it will straighten out the frequency. This will stabilize the frequency of an oscillator which is tending to drift with temperature. It's interesting. And we're at resonance. Resonance occurs when the capacitive reactance of a circuit is equal to the inductive reactance. Now, if you took those equations, where are they? There. If you set those two equal to each other, XC equals XL, you set both sides of those equal to one another and solve them, you will come up with this frequency. And that's the resonant frequency of that tank coil when you put them in either series or in parallel.
Well, and good, you're not getting into resistance tuning yet either.
No. Resonance is important in filters, tuners, antennas. This is why I'm putting it in the course, because of antennas. A series resonant circuit is very much equivalent to what happens in your antenna. A parallel resonant circuit of just inductance and capacitance is a great way to look at the final part of your antenna, your radio hooked up to the antenna. Because normally it would come out to a 50 ohm SO239. Yeah, SO239 is at 50 ohms. Normally on the inside of that, you have a coil. On the outside of that, if you have a dipole, you in effect have a capacitor. So you have a tuned circuit there, which if you want to do it properly and you feed 50 ohms and you want to have 50 ohm from your antenna, it's resonant. And you have in effect a capacitor. It will look rather like this. If you think of your AC source over here as your RF output from your radio, it would be hooked through that 100 millihenry coil, and then your 10 microfarad capacitor is your antenna. But for this application and for this resonance, this, I think it's 159 hertz. So those numbers are nothing like what you're going to have in a real antenna system. This is just an example that I stole. And I thought about working it out, and I went, not quite yet. We can do that later. So there I've repeated the equations again. Inductive reactance, capacitive reactance. Setting them equal, we get this. We simplify and we get our square root sign. And then we start working out. There's your 100 millihenry at 159.155 hertz. And you work out to 100 ohms. 100 ohms. Many times when you want to create a tank circuit in your radio, you want to have 100 ohms be the reactance. It's just kind of a rule of thumb when you're designing a circuit. If you change that frequency into something like in the 20 meter range or in the 144 megahertz range, then your inductance and capacitance will be very, very different. But you can do that at home. Wayne, you can do this in your head, right? Oh, come on, get out your calculator. You can do that. All you need to do is change the frequency there, and then you can fudge, as long as you work with 100 ohms as reactance, you can work backward and get the right inductance and the right capacitance. But what happens here is you look at the reactances and you put them into the E equals IR or E equals IZ format, and you put them together like they're in parallel, like they were in the circuit. Same thing as in resistance, 1 over 1 resistance, 1 over the other resistance, you add the inverse. Well, all of a sudden you see minus 90 degrees, plus 90 degrees. Oh, what happens here? We add those together and we get 0. Well, that's what happens at resonance. You're going to see slightly below resonance, it's going to be a very high impedance. And as you get closer and closer to resonance, the impedance just starts dropping like a rock. You hit resonance and it actually becomes 0. Right after resonance, as you raise the frequency some more, it's going to go up the other side again. So this is a parallel resonance. But you basically get free energy at that point from what it looks like, because you've got undefined, 1 over 0.
Are you talking about the current in the tank circuit?
Yes.
Parallel resonant tank, if you're talking about looking at the side
No, this is the
into it.
impedance. This is the impedance in there, and the impedance goes to 0.
In the tank.
The current would go to infinity.
But outside circuitry, looking at a parallel resonant tank.
You're not going to see the same thing.
No.
This is inside. This is kind of a magical thing that happens at resonance inside. Let's go through the next stage where you have series resonance. Think of this as the output of your radio into an antenna. You really want to add a resistor in there too, and that's where your radiation resistor or resistance comes from. You're always going to have some resistance, some inductance, some capacitance in every wire. But this is an antenna system with reactance. What happens when it goes resonant? All of a sudden, all that power shoots up amazingly, and you get great output. This is what you're doing when you're loading your antenna, when you're taking your MFJ tuner and you're all of a sudden tuning it. Look at the difference in power of just a few hertz difference. What we're doing, in effect, when we're tuning is we're changing the reactance of the system, not changing the frequency. But the same thing happens. All of a sudden, all your power goes to the antenna instead of burning up in the feed line or burning up on inside of your radio. This is your standing wave ratio, why you want to keep it lower. You get more power at the antenna, and it goes into radiation resistance instead of into your inductive or your capacitive reactance. You want it to go out. That way you get more radiation, and people hear you. So this is just the inverse of what happened back here. If I showed you the equation for this, or showed you the chart for this, you'd see a big dip right at resonance. In this case, you see a big peak. But this circuit is much more like your antenna system. The circuit before, back here, is much more like what happens in a tuner if you're trying to get a signal off of your antenna and tune it into the front end of your radio. Either one of these could be tunable. Normally we go with tunable capacitors, or in this day and age we have varactors, which are diodes which look like capacitors. But we want to vary one of these so we can then pick what frequency is actually going to come out. So your antenna system sees them all, and you only want to take what the tuner passes out. In a filter, if we're, do I want to go through local oscillator and mixers? No. If I want to filter out various frequencies.
This is about antennas, not about the radio control.
Not the whole thing. But if I want to filter out something and make sure only a small amount of the frequencies get through, I can use a circuit like this to do it. I could. I normally make it active and I'd use an op amp, but good. Keep your mouth shut. Applications of resonance. Well, I've gone through them, but a tuner, you can choose your frequency. You can choose the frequency from the whole radio spectrum. Your radio normally is either an HF or a medium frequency, low frequency, or a VHF or a UHF, so that kind of limits what's actually going to get in. But the front end of a radio almost always looks the same. You're going to see some form of tank coil, tank circuit in there with a tunable capacitor or even a tunable inductor. An antenna tuner is the same thing, only on the output. It can look the exact same way, and you're just trying to pick certain things to get through. Tank circuits stabilize oscillation. You can use them for filters or antenna tuners. In the next class, we are going to go through LC tuners, pi tuners, and Z-match tuners. Do you know what a Z-match tuner is?
Well, sounds like impedance matching.
Well, they're all impedance matching, but this one allows me to vary inductance by having two variable capacitors. So it's an LC that has two It's an LC2